Hey guys, welcome back to Practical Python. So what we have in front of us right now is a working bare bones PyTorch training loop. So we went over that in a previous video. So what it does is it will train the network to lower the loss as it goes over the data set, right? So I have three things that we can add in terms of functionality to kind of beef up this training loop. So the very first thing that we have is train test splitting the data set. And so what that does is reserve a portion of the data, never show it to the model, and we'll test the accuracy on that data to see if the model is generalizing to data it's never seen, or if it's just memorizing the examples we're giving it. So next, what we have is hyperparameter adjusting. So we'll go over some of the more key hyperparameters that will adjust how our model trains, and we can go over things like searching the hyperparameter space to see which set of hyperparameters is going to optimize our model the best. And finally, we can add some functionality in terms of how verbose the model's training loop is, so we can see some statistics as we're going through, which will be really important, for example, for finding those hyperparameters, and just to see how well our model performs after all is said and done, or in the middle of the training loop, etc. So let's go ahead and hit up this very first item, which is going to be splitting between a training and testing split. So all we have to do really to incorporate this into our data set is to add a flag to the data set that lets us know if we are training or if we're testing, right? So the default will be that we are training the model. And then let's add another parameter that will be percent of data that we're going to use to test the model. So we'll use 0.5 for that. And so the idea here is after we've added all the data, if we're training, we'll take the first 95% of the data. And if we are testing, we'll just take the last 5%, right? So what we'll do here is just say self.x equals up to 95, or we'll say 1 minus percent test times the length of x. So this will take 95% of the x values, and we'll just do the same for the y values. And then we can just take this code and say otherwise we'll just take starting from that same index and going on. All right, so here now we've effectively made it so that we can split our data. All right, so let's just go ahead and test this, make sure this functionality is working properly. So let's open up a little Python shell and import. All right, so now let's see if the train data set is the proper length. So we'll just initialize this with train. All right. Okay, that's looking promising. And now let's just make a validation data set and check. There we go. All right. So now that has perfectly split our data into a train and test split. So again, what we can do is make a determination of how well our model is actually learning. So now to actually incorporate this, what we're going to want to do is let's make two data sets, the train data set and the test data set, and make our data loader for each as well, so that way it can feed data. So this one again is going to be the test, and this doesn't matter, but whatever. All right, so we'll go over just the test. No, this should be train. So we'll go over just the training data at first, right? But then after that, we'll go over the test data set now, right? And so it's going to be basically the exact same loop, except we're not messing with the optimizer and we're not messing with the loss. I'm just going to be tracking the accuracy. So we can actually just copy all these over. These will be exactly the same. Send the prediction through the network. And we can just go straight to getting this accuracy here, right? And so let's not print it out here. Let's actually print out, right, the one we kind of care about, which is if the model can extrapolate to data it hasn't seen before, right? And so just to recap, we're going over the training data and actually training on it. And then we'll go over the test data and only check the accuracy on these. And one more thing we're going to do, two more things actually. We don't care about propagating the gradient through the model, and we want our model to be in eval mode. Which I don't think any of the parameters for this model are actually affected by that, but it's just best practice to transit between this eval mode for when we actually care about using the model, and then putting it back in train mode. All right, so let's just go ahead and add one more thing. So we'll keep an average of all the accuracies. So train accuracy is going to be 0. Or better yet, let's make these lists. Test accuracy. Right. And now let's just get the accuracy here and add it to the respective list. So each time we go through, we'll be tracking the accuracy of inside the training loop. And this one will be tracking the test accuracy. And at the end of each epoch, let's go ahead and print the train accuracy. And that's just going to be the average, just the sum over the length. And we can just copy that as the test accuracy, which is going to be test accuracy sum over test accuracy length. All right, now let's go ahead and run this code. Let us know which epoch we're in. All right, so let's go ahead and run this training loop and see how the training accuracy compares with the test accuracy. All right, so check that out. So what we've seen is that the training accuracy is generally trending with the test accuracy, which is good. That means the model has not begun to overfit and memorize on the data. So what that indicates is that we can probably increase the number of epochs we're running until we see an inflection here, right? And so we haven't quite gotten there, but it's starting to bottom out on that exponential curve, that inverse exponential curve of our accuracy, right? So that's going to kind of level off. All right, so that's a very important concept to go over. Next, let's go over our hyperparameters, right? So the main hyperparameters we have that are just right off the bat going to have one of the largest effects are the batch size and the learning rate, right? So what the learning rate does is tells all the parameters inside of the model how much to change based off of the loss we have calculated right here, right? Right. So the loss is going to tell us how far these two values differ, and then the learning rate is going to tell you how much we should nudge the parameters, all those different neurons inside of our network each time. Because if you push them too far in one direction, they'll oscillate and they'll never converge, right? So if we put this all the way up to say 0.1 and ran the model, let's go ahead and see how that looks. All right, so I went ahead and put the neural network and all the data onto the GPU just to speed training up. But as you can see, by increasing that learning rate, we've actually made our accuracy worse. It does not improve because, again, we're kicking around those parameters, and they'll never get the chance to dial in on exactly what values they should be to start minimizing the loss, right? So similarly, if we set our learning rate very low, what's going to happen is our model's going to take forever to update the parameters, right? It will never overshoot, but it will also take way too long to get there. So let's go ahead and run this and see how that accuracy changes over these 10 epochs. All right, so you can see that having the learning rate too low will also cause the model not to learn anything, right? It's taking way too long to update those parameters. We'd have to go just epochs and epochs and epochs in order to actually meaningfully change the models, right? So just to show you that, again, this is all the learning rate. We put it back to, let's say, a good value, 0.0002. We only get up to about a 31% accuracy, but if we keep going in epochs and see the data more times, right, we might be able to dial in a more precise manner than our previous learning rate of 0.001. So the learning rate is one of the most important hyperparameters, but what else we have is the batch size, right? So the batch size determines how many of our data points are going through the model before it makes an update to its parameters. So this is important because it plays hand in hand with the learning rate, right? If we're seeing 1,024 data points at once, that means we're only updating the model parameters, the length of our data set over 1024, right? So these two kind of play hand in hand. So if we increase the batch size, let's go way up. What's going to happen is we're going to make fewer and fewer updates to the model parameters, right? So let's just go ahead and watch that in action, right? Right. So check that out. We ended with about 2/3 of the accuracy we did with our previous run. All right. So the flip side of having a larger batch size is that the error we get from running 8,000 examples through the model is going to be more precise than if we ran 1,000 samples through the model, right? So what having a larger batch size can let you do is increase that learning rate, because it's not going to set you onto a path that's as noisy as if you're using smaller samples, right? So those are the two most important things to pay attention to in your training, is that learning rate and the batch size. Some other things that we could just go over real quick. We have weight decay, and what weight decay is going to do is add a penalty, usually about 0.01, 0.1. It's going to add a penalty to the model choosing to update the weights. And so what that's going to do is bias the model less towards changing the weights and kind of settle in on the current parameters it has. Another thing we have are these betas. And so what these are going to affect, and this is only for the Atom optimizer, what these are going to affect are essentially how much momentum the optimizer is carrying forward from previous examples, right? So essentially what it lets you do is, if you have the same error showing up multiple times over the examples, it's a good bet that you need to update that a lot. All right, so now that we have a couple hyperparameters to play with, let's actually go over running a grid search to see which set of hyperparameters is going to give us the best training results, right? So really you could just nest for loops and say we'll vary the batch size from between, let's go, 64, 1024, and 8192. And we'll also vary the learning rate from 1 times 10 to the negative 2, negative 3, and negative 4. Right, so we'll test all of these. And then let's just go ahead and make a stats dictionary. All right, say our key is going to equal batch size, learning rate. All right, and let's not print this value out. What we're going to do is say at the end of that training iteration, so going through every one of those epochs, we'll say stats for our key is going to equal a tuple of whatever training accuracy we ended up with and whatever testing accuracy we ended up with, right? So now what this is going to do is let's go ahead and print out that dictionary at the end and see which of these combinations, right, which batch size matched with which learning rate is going to raise our model's accuracy the most over 10 epochs. So let's go ahead and run that and see what we end up with. All right, so check it out. We got our results back, and here's our winner here, right? So we had the highest validation accuracy on the 1024 by 0.01 learning rate. Now, this was not a super rigorous test, right? We should have tested for more epochs, changed potentially some other hyperparameters, but this type of grid search here is a good way to just see how your hyperparameters are going to influence your training, right? So you can run one of these in your training horizons. Is going to dictate really how well these results extrapolate out, right? So I mean, we got the best accuracy on the largest learning rate, right? So if we extended this out to more epochs, maybe we'll see that this doesn't end up generalizing as well as like maybe this next one here, right? But this is a good rough technique that you can be incorporating. All right, so let's go ahead and jump into the final thing we have here. So I'm just going to reset this real quick. And all right, the last thing that we can do now is just increase the verbosity of the model and print out some more status updates as we go, right? So one thing we can do is we can, every few batches or so, print out the test, right? So a common thing, if let's say I is, let's say every 10th batch, then we can go ahead and print those statistics. Right, there we go. And another thing, let's print out what epoch we're on. And then let's finally print out our very last test result. So we can go test accuracy. All right, so now we'll get more of a finger on the heartbeat of the model as it's running through all the batches, right? So now you can see, we can see how much the loss changes from the beginning to the end. Sorry, this wasn't loss, this was accuracy. Right, so now we can see how the accuracy is changing from one epoch to another, and then we can compare to that final test value, right? Another thing we can do is plot these against each other, right? Because again, what we're looking for is an inflection in the test accuracy to where we're no longer getting better at predicting those values we haven't seen, right? So we'll go ahead and we already have the plot. So now let's just go ahead and track all these values for the duration. So let's pull these outside of the epoch. And so now this is just keeping track of all accuracies throughout the entire training pipeline, right? So now what we're going to go ahead and do is just plot those. So we'll plot the training accuracy, and then we'll go ahead and plot the test accuracy. And this is just going to give us a nice visual outlook on how the model's doing. Just add the legend. Right, and then a nice show. All right, so here we have it. We have our accuracy over batch, right? And so what you can see is that the test accuracy and that training accuracy are both continuing to trend with each other, which means that we can keep training this model before we get overfitting, right? So let's just go ahead and run this for a few more epochs and get a visual of what that would look like. All right, so here you can see I ran 150 epochs, and it turns out that the test and the training accuracy actually tracked the whole way, and we had meaningful progress throughout the entire training curve. And that's actually a good thing to see. You can kind of see how the training kind of plateaus here. So if you're making like an efficiency determination, you probably cut it off here and say this is around where we'd like to train the model, right? You can always throw more compute at it, but these hyperparameters and the tracking of the accuracy looks good here. So there you have it. We went through 3 things today that you can do to spice up your PyTorch training loops. You can split your data into test and train, which is always a good idea. You can look at the different hyperparameters and search that parameter space in order to find what leads to the best results. And you can insert some statistics as you're training along the way and really get some good visualizations of the results. Thanks for making it this far. Drop a like if this video was useful. Put in some comments what you're planning to build. I'll see you guys next time.